A rectangular garden is to be constructed using a rock wall as one side of the garden and wire fencing for the other three sides. Given 150 feet of wire fencing, determine the dimensions that would create a garden of maximum area. What is the maximum area? Alright, so let's start by drawing a diagram. So this will be the rock wall, and this will be the rectangular garden, and we could label this as X and Y. And we're given that there's 150 feet of wire fencing to be used. So let's call the total amount of wire fencing T, and that would be equal to Y plus 2X, because we're adding up these three sides. And the question's asking us what's the max area. So the area of this rectangular space would be area equals xy. So we're trying to maximize the amount of area given the total amount of fence. So eventually we're going to have to take the derivative of this to find the critical points. So the total amount of fence is 150 equals y plus 2x. So you could isolate for x or y, but let's just isolate for y because it's easier. So y equals 150 minus 2x. So if we're going to take the derivative here, we need it in terms of one variable. So we could sub in this y equation into the area equation. So we're going to get area equals x times 150 minus 2x. And we could just expand. So now we're going to derive the area equation to get the critical points. So a prime equals 150 minus 4x. And the critical points occur when the first derivative is equal to 0. So we're going to get equals 0, 4x equals 150, x equals 37.5. So we're going to do the second derivative test to confirm this is the maximum critical point. So we're going to get negative 4. And since the second derivative is negative, this means that we're going to have a maximum. Because if it's concave down, that means this critical point will be the maximum. So now that we have x, we're going to use our original equation to find y. So y equals 150 minus 2 times 37.5. And we're going to get 75. So area equals x times y. So we're going to plug in 37.5 times 75 equals 2,812.5. So this is the maximum area that we could make with 150 feet of fencing. And the x and y are the dimensions of the garden. A fence is to be built to enclose a rectangular area of 300 square feet. The fence along three sides is to be made of material that costs $7 per foot, and the material for the fourth side costs $12 per foot. Find the dimensions of the enclosure that is cheapest. So let's just draw our rectangle, and it says that the total area is 300 square feet. So let's just say that this side is the one that costs $12 per foot, and these other three sides cost $7 per foot from here. So again, we'll just label the rectangle as X and Y. So the question's asking for the dimensions that would make this enclosure the cheapest. So if we're looking to optimize the cost, we're going to need a cost function. So in this case, it would be cost equals $12 times this Y length plus $7 times 2x plus y. So this will be the cost of the entire rectangle. So let's just simplify. Again, we have the cost in terms of two variables, so we're going to want to sub in one or the other to only have it in terms of one variable. So we can use this restriction of 300 square feet of area to find that. So the area will just be x times y, and it says we have 300 square feet of area. So let's just isolate for x, and we're going to get x equals 300y. So now we could just sub that in to here. So cost equals 19y plus 14, 300 divided by y. Let's simplify. So c equals 19y plus 4,200 y to the negative 1. So recall that if you have 1 over y, it's the same as writing y to the negative 1. It's just easier to do the derivative that way. So now let's derive this. We're going to get 19 plus negative 4,200 y to the negative 2. Now to find the critical points of cost, we're going to set this equal to 0 and solve for y. So we're going to get 19 equals 4,200 over y squared. Y equals root 4,200 over 19. So if you plug that in, you're going to get 14.86 feet. And because of the square root, it could be positive or negative, but there's no such thing as a negative side length, so we're just going to take the positive one. Now to confirm this wide length will minimize the cost, we're going to take the second derivative of cost. So we're going to get 8,400 times y to the negative 3. And if we plug in 14.86, we're going to get 2.56, which is a positive number. So we know that this will minimize the cost. So now that we confirmed the y value is correct, we could plug it in over here to find x, and you'll get 20.18 feet. And to confirm this is right, we could solve for area and make sure it's 300. And again, if you plug that in, you'll get 300, so we know it's correct. So our final answer would be x equals 20.18 and y equals 14.86. Jake wants to build a garden fence to protect the rectangular 500 square foot planting area. His next door neighbor agrees to pay for half of the fence that borders his property. Sam will pay the rest of the cost. What are the dimensions of the planting area that will minimize Jake's cost to build the fence? So let's say this is the garden fence, and the neighbor will pay for half of this side. So we could just label it X, Y. So the question doesn't give us how much the fence costs per foot, so we're just gonna let Z equals cost per foot. The question gives us that the rectangular planting area is 500 feet squared. And the question's asking for the dimensions of the planting area that will minimize Jake's cost to build the fence. So the total cost that Jake's going to have to pay is going to be the cost per foot times 2x plus y. So this is accounting for the three side lengths that the neighbor isn't paying half for. Then it's going to be plus z times y divided by 2, because the other half the neighbor's paying for only this side length. And the total area is going to be x times y equals 500. So we know we're going to have to sub something in, so let's just isolate for x. And we're going to get 500 divided by y. We could expand and we're going to get 2cx plus zy plus zy over 2. So now we could just sub in x. So we're going to get 2z times 500y plus zy plus zy over 2. And we could just simplify. So we're going to get 1000 z over y plus 3 over 2 zy. And we're just going to bring this y to the top. -1 plus 3 over 2 zy. So it looks a bit confusing because we have two variables still, but this variable we're going to treat as a constant. So when we derive it, it'll be the same. So let's take the derivative, and we're going to get -1000 z y to the -2 plus 3 over 2 z. So now we're going to set this equal to 0 to find the critical points. And bringing this over to the other side, we're going to get 3 over 2 z equals 1000 zy to the -2. And you'll notice that the z's are going to cancel out. So we're going to get y squared equals 2 over 3 times 1000. And we could take the square root. And we're going to get 25.82 feet. Again, this could be positive or negative, but we're going to ignore the negative side length because it's not possible. Now again, we're going to take the second derivative to confirm the answer. So c prime prime is going to be 2000 zy to the -3. And we're going to plug in y equals 25.82. And it's going to be 2000 z over 25.82 cubed. And we're going to get a positive number, meaning this critical point will minimize Jake's cost. Because the cost function at this point will be concave up, confirming that it will be a minimal cost. Now that we confirm that, we could find x using this equation. And we're going to get 500 divided by 25.82 equals 19.36 feet. And again, let's confirm that when you multiply x and y, it'll equal 500. So area equals x times y. So 19.36 times 25.82. And we're going to get 500. So now that we confirmed our answer, our final answer will be x equals 19.36 and y equals 25.82 feet to minimize the cost.